Ever iced a cake? A 3D printer does the same move. It draws one paper-thin slice, then another, until a solid shape appears. How does that not fall apart? Let's pull the cover off the trick, layer by layer. Your phone case, a dental aligner mold, even parts inside a jet engine can be made this way. Each one is a stack of thin layers that you cannot peel apart. A 10-centimeter tall print at 0.2 millimeters is 500 layers. Picture laminating 500 clear films into one block. The whole game is to make those films fuse so well they act like one solid. Here is the first catch. The printer does not really know 3D. It only draws flat lines on a plane, then lifts a tiny bit in Z and repeats. Slices fake the third dimension. Gravity and cooling fight you while you fake it. Overhangs can sag in midair. Plastics shrink and warp as they cool. Resin wants to stick to the window at the bottom of the vat. The hidden hard part is planning paths that both support themselves and fuse. The brain that does this planning is slicing software. Cura and Prusa Slicer are common picks. They take your model and split each layer into perimeters and infill. Perimeters draw the outer walls. Infill is a light lattice inside. The software turns paths into a long list of moves called G-code. Lines like G1 with X, Y, Z, E, and F tell motors where to go, how much plastic to push, and how fast. Thousands of tiny moves draw each layer. Then the machine takes one small step up. Most home printers use material extrusion, often called FDM. Think of a robot icing bag. A 1.75 millimeter plastic filament feeds into a hot end. It melts and squeezes out of a 0.4 millimeter nozzle at roughly 190 to 260 degrees Celsius, depending on the plastic. Layer height sets the look and the time. 0.05 to 0.30 millimeters is typical. Thinner looks smoother, but takes longer. Stepper motors move the head in tiny bites. A common stepper motor turns 1.8 degrees per full step. With microstepping and GT2 belts, the head can move in very fine nibbles, around hundredths of a millimeter per microstep on many rigs. That number sounds precise, but it is not the whole story. Real accuracy depends on belts, friction, flex, and how the firmware plans motion. The point is simple. The machine can place plastic very, very consistently when tuned well. Watch one layer get built. The printer draws the perimeters first for a clean shell. Then it fills the middle with a lattice. 10 to 30% infill is common for everyday parts. Supports hold up big overhangs. A simple rule helps. About 45 degrees from vertical will print without support. Short bridges, maybe 10 to 20 millimeters, can work too with good cooling. A warm bed keeps the first layers stuck down. A part fan hardens fresh plastic so it does not droop. The print is only as good as the first layer. Bed heat helps plastic grip and reduces warping. Rough numbers help you start. PLA likes about 50 to 60 degrees. PETG prefers 70 to 90. ABS wants 90 to 110. Clean the bed, level it. Set a squish that makes the first line look like a short oval, not a round string. Once those first roads hold, the rest of the build has a solid base. Strength comes from welding beads together, not just stacking them. When two hot plastic roads touch, their polymer chains wiggle across the boundary and tie knots. That takes heat and a bit of time. If you print too cold or too fast, layers do not bond well. Along the layers is usually stronger. Across layers in Z can be only about 50 to 70% of that. Turn parts so the main forces run along the layers when you can. Filament tolerance and vibration change how smooth lines look. Slower outer walls often look cleaner. More shells can boost strength where bolts clamp or parts rub. But solid is not always better. Shells with around 20% infill are strong enough for many parts and save time and plastic. Pick infill patterns for the job. Grid and gyroid are popular. Think about where screws go, where stress flows, and which faces you see. There is a whole other branch that does not use filament. Resin printers build entire layers at once with light. An LCD masks UV into a pattern that cures a thin slice of liquid. The part hangs upside down from a plate. Typical pixels are 35 to 50 microns. Layer heights are 25 to 100 microns. Each layer cures in 2 to 8 seconds. Build time scales with height, not with how busy the slice looks. Each new resin layer has to peel off a clear window at the bottom. That is a gentle flex and lift move. After the print, the part is wet and sticky. You wash it in isopropyl alcohol, then cure it under UV to reach full strength. Use gloves and eye protection. Treat liquid resin in soaked towels as hazardous until cured. The finish can be very sharp, which is why miniatures and dental molds love this method. Powder bed nylon is called selective laser sintering. A laser draws in a warm bed of nylon powder that sits near 170 to 190 degrees. Where the beam hits, the powder fuses into solid. The loose powder around it cradles overhangs, so most shapes need no support. Parts cool in the bed, then get brushed or vacuumed clean. Accuracy around plus or minus 0.2 to 0.3 millimeters is common. Metal powder bed fusion lays down a thin layer of metal powder. A strong laser melts the slice in an inert gas chamber. Layers can be 20 to 60 microns thick. Laser power is a few hundred watts. The plate is heated, often 80 to 200 degrees, to tame stress. You remove supports and often heat treat the build. Then you machine faces that must be very flat or smooth. The shapes you get can be wild and very strong. Here is a famous example. GE turned more than 20 small fuel nozzle parts into one printed cobalt chrome piece. The printed nozzle has internal channels that snake in ways normal machining hates. It cut weight, improved durability, and entered service in 2016. By now, tens of thousands have flown. This is additive doing what it does best. It makes one complex part instead of many simple ones that must be joined. Step back and watch the motion. A print is thousands of two-dimensional moves, plus tiny steps in Z. That is it. From those slices, a three-dimensional shape appears. Typical FDM speeds are 40 to 100 millimeters per second. A 10-centimeter tall part at 0.2 millimeters with 3 perimeters and 20% infill can take 4 to 8 hours. Inside a fist-sized part, there can be tens of meters of thin plastic roads. In 1984, Chuck Hull invented stereolithography. He later founded 3D Systems in 1986 and kicked off commercial 3D printing. Years later, ISO and ASTM wrote down a shared language. One key standard, 52900, lists 7 additive families like extrusion, that photopolymerization, and powder bed fusion. In 2005, the RepRap project shared open-source printer designs. That move lit the fuse on home and prosumer machines across the world. So how do you master the slice? Turn parts so loads run along the layers. Respect the 45-degree rule. Use supports only where needed. Keep bridges short and cool them well. Plan holes upright when you can. Put nice faces on the top or sides, not on the bottom over supports. These choices decide if your part looks clean and holds up under use. Small tweaks make big gains. Lower layer height smooths curves but adds time. Higher nozzle temperature improves bonding, up to the point where details blur. More cooling sharpens bridges, but can cause warping or weak layers if overdone. Slow down perimeters to improve finish. Speed up infill to save time. Change shells where bolts clamp. Adjust flow if first layers look thin or fat. A few runs on a small test part teach fast. Resin is hazardous until cured. Wear gloves and eye protection and cure waste before you toss it. Food-safe claims for common FDM plastics can be misleading. Tiny pores and pigments can trap bacteria unless the part is sealed and sanitized. Strength and accuracy numbers vary by machine, setup, and material. Microstep size is not guaranteed accuracy. Belts, backlash, and motion planning all play roles. Treat specs as guides, not promises. Here is a quiet win you may not see. Dental labs print resin molds by the thousands every day, then heat clear plastic over them to make aligners. On the hobby side, volunteers used home printers in 2020 to churn out face shield frames in garages and schools. Layer by layer can scale from your desk to a factory line when the job fits the tool. Let's zoom back to the cake. A 10-centimeter object is 500 laminated films. Each track is narrower than a strand of spaghetti, yet the stack behaves like one piece. The trick is not magic. It is time, temperature, and motion, repeated with patience. Once you see that, impossible shapes start to look very normal. If this is clicking, you will enjoy the rest of Buildguts. We love the inner machinery of everyday tech. Subscribe if you want more clear, satisfying explainers like this. Drop a like if this helped you. There are deep dives on chips, planes, bridges, and the power grid waiting on the channel. Thanks for hanging out, and see you next time.